Here we have the graph of y equals x squared between 0 and 1. Finding the area under the curve is simple, as the integral of x squared is just x cubed over 3 evaluated from 0 to 1, which is 1 over 3. But what if we try to evaluate this integral in a slightly different way? Suppose we have a general function f of x, which we want to integrate between 0 and 1, and big X is a random variable that is uniformly distributed between 0 and 1. Also, the random variable y is defined to be f of the random variable big X. The expected value of y is the same as the expected value of f of big X, which is the total of f of little x times the probability that big X equals little x over all of the values that big X can take. This is precisely the integral between 0 and 1 of the previously mentioned function. Noting that from the definition of a uniform distribution, we know that the probability that big X equals little x is equal to 1 for all of the values of little x between 0 and 1. Thus, the expected value of f of big X is precisely the integral that we started with. This means that using the example we had before, if we used enough randomly chosen values between 0 and 1, put them through the function f, and then took their average, we could find the value of the integral that we evaluated at the beginning of the video. Let's try it. Once again, we have the graph of f of x equals x squared between 0 and 1. And we want to find the integral, but we will do it using the random point method that we just looked at. You might want to keep track of the estimated value of the integral, which updates every time we add new points. We have only sampled around 100 points, but this has given us a very accurate estimation of the integral, which is only around 1% off the true value. Did you notice that the estimated value got closer and closer to the true value as the number of points increased? This is an extremely important observation known as the law of large numbers, and can help us to obtain an approximation of pi later on. But first, let's consider a unit quarter circle, and we will estimate its area using Riemann rectangles. As the number of rectangles increases, the area of the quarter circle seems to approach a certain irrational number. Let's call this pi over 4, so that pi would be the area of the whole unit circle. Now, moving on to a more general quarter circle with radius r, we propose that the area of our quarter circle is pi r squared divided by 4. As in a square, for example, the scale factor is the square of the side length, so we would naturally suspect that the area of a circle is proportional to the square of its radius. Now we just want to find this constant of proportionality, which we have called pi. We will achieve this by running a mini Monte Carlo simulation. To do so, we must acknowledge the square which contains our quarter circle, with its area being r squared. This is our plan. We will randomly generate a large number of points which are within our square. Since the points are uniformly distributed across the plane, the number of points inside the quarter circle divided by the total number of points approximates the area of the quarter circle divided by the area of the square. After some simplification, we can see that the number of points inside the quarter circle over the total number of points approximates the value of pi over 4. In addition to that being extremely cool on its own, we can deduce that this approximation gets more and more accurate as the number of points increases, due to the law of large numbers which we came across earlier when observing that the estimate of the integral was closer to its true value as the sample size increased. And who would have thought the percentage error of our final estimate of pi is under 1%. Just imagine how accurate it could be if we used 10 times more points. Okay, I know what you're thinking. That approximation of pi wasn't that good. I mean, it's not even accurate at 2 decimal places. So I made this little Python program here, which outputs an approximation of pi that's accurate to 5 decimal places, with an extremely low percentage error, checking 100 billion data points. I think this shows that the law of large numbers is extremely important, and that Monte Carlo simulations can be quite accurate, but you just need an extremely large sample size and a lot of computing.